Hello everyone, this is Prateek Rajpoot, a final year BTech student of Faculty of Engineering and Technology, University of Lucknow, and I shall be presenting my seminar presentation on the topic viaducts. Here is the table of content that includes introduction, need for viaducts, history of viaducts, case study 1, and finally the case study 2. Now move on to the introduction. A viaduct is a long bridge-like structure that connects two elevated points such as a valley, gorge, or body of water to carry road or rail traffic. The term viaduct is derived from the Latin words via, that means roads, and ducere, that means to lead. Moving on to the need for viaducts. Viaducts are basically needed to carry a road or railway over an obstacle, such as a river, valley, or another road. They also keep traffic from being interrupted by other traffic, such as trains on a railroad. Also provide straighter and flatter routes for rail traffic and can also cross over roads in settled areas. Moving on to the history of viaducts. The history of viaducts can be traced back to the Roman era when engineers developed them to carry water across long distances. The earliest were the Roman aqueducts that were made up of a series of arches supported by stone or masonry piers. Sankey Viaduct, built between 1828 and 1830 in Newton Levelos, England, was the world's first major railway viaduct. Moving on to the recent developments, Basics and Ney and partners took up the challenge and designed the circular arch viaduct, an innovative system that is completely demountable and reusable. Compared to a conventional viaduct, the concept uses drastically few raw materials. Next up is the building information modeling. This technology pairs architects, engineers, and construction professionals to improve communication and collaboration. BIM allows engineers and designers to create 3D models with lots of data. Next up is the double composite design. This design uses a concrete bottom to steel beams to create a hollow box structure. This reduces the use of concrete and steel and allows for longer spans between piers. The HS2 project is using this design on 5 viaducts in Buckinghamshire, Oxfordshire, and West Northants. Here comes the first of our case studies, the Millau Viaduct in France. These are the specs of the Millau Viaduct. Height at 343 meters, the Millau Viaduct is the tallest bridge in the world and is about 20 meters taller than the Eiffel Tower. The Millau Viaduct is around 2460 meters long. Its deck is 11 meters deep and made of hollow steel and supported by 154 cables from 7 steel pylons. The pylons are 87 meters high, which is the height of a 29-story building. It rests on 7 concrete piers, each weighing 650 tons, and is shaped like an inverted trapezoid with sloped sides. And the total cost of the project was 400 million euros. This is a picture depicting the Millau Viaduct. Now we shall move on to the construction. The deck of the viaduct was prefabricated in box sections at the Eiffel factory in Alsace, then transported to the construction site by barge and road. Meter high steel pylons were moved into their place on hydraulic transporters. The road deck was constructed on plateaus at either end of the viaduct, then pushed onto the pylons using hydraulic jacks, and the superstructure was assembled into 2 sections, one on each side of the valley. The construction was constructed high over the gorge valley using a series of computer-controlled hydraulic platforms. A 2-headed welding robot was also used, and a 160-ton auto-lifting trailer and automatic laser tachymeters were used in the construction of the deck. The challenges faced in construction. The weather was affected by extreme weather conditions such as strong winds and low clouds. The installation was also a major problem. The viaduct deck was 2.4 kilometers long, weighed 36,000 tons, and was 245 meters high. The construction company had to pre-assemble the deck elements on safe ground and then push them over each pier to the middle. This was a risky proposal that had never been attempted before on the scale. It was complex to procure materials and establish construction methods for such a large project. The erection of steel pylons was also a difficulty, as they were to be moved out from each bank and erected on the deck at each concrete pier. The construction time was also less. The prime contractor was challenged to complete the structure in record time of just 3 years. Up next are the innovations in construction. The superstructure was assembled in two sections, one on each side of the valley, and then launched out over the piers. The deck was made of steel instead of concrete to provide additional support. Each column splits into two thinner, more flexible columns below the roadway to accommodate the expansion and contraction of the concrete deck. The tapered form of the columns minimizes their profile in elevation and expresses their structural load. We shall now discuss the impact and significance of the Millau Viaduct. The viaduct has reduced traffic congestion for drivers traveling from northern France to the Mediterranean coast, cutting travel times from hours to minutes. It has also become a major tourist attraction, with visitors able to walk around the base of the piers and take a boat ride under it. The viaduct has had a lasting impact on the local economy, including the creation of new businesses and an expansion of tourist options. Its construction was designed to minimize its impact on the surrounding environment. Moving on to the second case study, the Colne Valley Viaduct in the United Kingdom. Moving on to the introduction of the Colne Valley Viaduct. The Colne Valley Viaduct is 3.4 kilometers long and it crosses the Colne Valley, a public space with parks, reservoirs, and the River Colne on the northern west outskirts of London. It also carries the high-speed 2 railway, which will connect London and Birmingham, and the trains travel up to a speed of 200 miles per hour. The viaduct's 1,000 precast segments were made on site at a purpose-built factory, and it was completed on the September 5th, 2024. These are the pictures depicting the Colne Valley Viaduct and the route plan of the Colne Valley Viaduct. Moving on to the construction of the Colne Valley Viaduct. The first is shock absorber units. To appropriately handle rail braking loads of up to 9,000 tons, a total of 4 shock absorber units were integrated into the deck structure of the viaduct. It also consists of The foundations consist of driven piles upon which the faceted framework is installed. To reduce its impact upon wildlife and the general public alike, 4-meter high translucent acoustic barriers were installed along the entire length of the viaduct. These will reduce noise emissions while only incurring a minimal impact upon the view of onboard passengers. In total, 908 deck units and 92 pierhead units were produced, weighing between 60 and 140 tons, each one unique to its intended place in the overall structure. Moving on to the challenges faced in the construction of the Colne Valley Viaduct. The viaduct is in a sensitive landscape with ancient woodland, triple SIs, and multiple water bodies. To minimize the impact on the environment, the design reduced the width of the structure and its construction corridor. The viaduct had to accommodate the structural loads of high-speed trains traveling up to 320 km per hour, and the viaduct's location and tricky terrain presented challenges. Providing safe access for plant equipment and materials was a challenge. The viaduct had to balance the needs of the client and local community stakeholders. These are the innovations in the construction of the Colne Valley Viaduct. The first is the launch girder. A 700-ton launch girder, the one of its only kind in the United Kingdom, assembled giant precast concrete systems to form the first kilometer of the viaduct deck along the edge of the valley. The first enormous V-shaped piers were completed in the lake to allow the viaduct to curve eastward over the water. The V piers, each weighing around 1800 tons, support a row of arches inspired by the flight of a stone skimming over the surface of the water. A total of 11 V piers support the viaduct. To hold back water during the construction, cofferdams were used to hold back the water while 60-meter deep foundations were built into the bed of the lake. We shall now discover the impact and significance of the Colne Valley Viaduct, the first being improved travel. The viaduct will significantly reduce journey times between London and Birmingham. It will also set a free space on the existing mainline for more local and freight services. Carbon footprint has also been reduced through structural deficiency, reduced massing, and cement replacement. The viaduct was designed to meet technical, environmental, and operational requirements while also responding to the landscape setting. The design includes spans up to 80 meters long, a curved soffit to give the appearance of arches or skimming stones, inclined panels to break the depth of the deck. We shall now put an end to this presentation with the references. These were the references that were used to gather the data for the foreshown presentation.